All right, here we have analyzed a chemical that is used in photographic developing fluid and found that it has a composition that is 65.45% carbon. It is 5.45% hydrogen and 29.09% oxygen. Okay, it says if the chemical's molar mass is blah blah blah, what's its molecular formula? Again, in order to find the molecular formula, you must first find the empirical formula. So I'm going to do this again by just assuming 100 grams of my sample to get out of the percentages. So it's going to give me 65.45 grams of carbon. It's going to give me 5.45 grams of hydrogen and 29.09 grams of oxygen. I can get them all into moles. So 1 mole of carbon is 12.01 grams. So my grams cancel and I'm left in moles of carbon. Okay, so I'm in green again, so I'm going to just do this. So 1 mole of oxygen is 16 grams of oxygen. So my grams cancel and I'm in moles of oxygen. And here I've got 1 mole of hydrogen is 1.01 grams of hydrogen. I'm left in moles of hydrogen. Okay, let's do the math. So I've got 65.45 divided by 12.01. Okay, I get 5.4500. The reason I chose to round that up, if you look here, okay, I would have, well, actually I could have just done that. Sorry, I was looking at doing rounding that 9 up. Let's go ahead and write this out. Sorry, that was my fault. So 5.4496, that 2 does not round that 6 up, excuse me. So 5.4496 moles of carbon. Okay, for hydrogen, I've got 5.45 divided by 1.01. So it gives me 5.3960. Again, that 3 would not round that 0 up. And then for oxygen, I've got 29.09 divided by 16. And I get 1.8181. That's a fun number. It's like a palindrome number too. All right. Again, I'm going to divide by the least number of moles so that way I can get their ratio to each other. So I'm going to divide everything by 1.8181. Okay, I'm going to use orange just so that you can see everything. Okay. I know this is just going to give me 1 mole of oxygen. Okay. For carbon, I've got 5.4496 divided by 1.8181. So 3 moles of carbon. And here I've got 5.3960 divided by 1.8181. This gives me also 3, so 2.9 something. It's going to round up to 3. Okay, so my empirical formula is going to be C3H3O. All right. Again, to find the molar mass, you got to see how, or to find the molecular formula, excuse me, you got to use the molar mass of the actual compound and see its relationship to the molar mass of your empirical formula for that compound. Okay, so I'm going to take carbon, hydrogen, and oxygen. I've got 12.01 times 3, so 36.03 grams per mole for carbon. Okay, I've got 1.01 times 3, so 3.03 grams per mole from hydrogen, and 16 on the dot times 1, grams per mole for oxygen. Okay, if I add that up, so add up there, I'm going to get, let's see, so something 0.06, 9, 15, so 55.06 grams per mole. Okay. All right. Now I can say that X times my empirical formula is equal to my molecular formula. I can divide the molar masses of my empirical and molecular formulas to find that multiple. Okay, I know my molecular formula has a molar mass of 110.0 grams per mole. And here I've got 55.06 grams per mole. My units will cancel. And again, this should be about 2. So divided by 55.06. And I get 1.997. This is just because of rounding. That is 2. So my molecular formula is going to be twice this large. So C6H6O2. Okay, so this is my molecular formula. I notice here how all of my examples so far, the molecular formula has been twice as large as the empirical formula. That is not always the case. It just so happened to work out that way for my examples. You'll see in class, on an exam, and in many, many other example problems that is not always the ratio. It's not always 2 to 1. But at least you know how to do the math to find it.